The last time we met together in class, we were talking about discrete random variables and what the probability distribution table looks like, and a couple examples of discrete random variables. So I'm going to skip past the first part of this document. We also talked about how to find the mean of a discrete random variable and how to find the standard deviation or variance of a discrete random variable. So we have formulas for all that. So the second part of chapter 5 is on one particular discrete random variable, which is called the binomial random variable. And the binomial random variable arises in the following situation. There's a fixed number of n, lowercase n, independent trials. Each trial has two outcomes, which statisticians refer to as success and failure. The probability of success, which we indicate with a lowercase p, remains constant from trial to trial. And also, since there's only two outcomes on each trial, the probability of failure is 1 minus p. And then we have a random variable x that's counting the number of successes in the n trials. If all of those criteria are met, then x is considered a binomial random variable, and it has this probability function. So this is a function or a formula that will help us find the probability of a certain number of successes. The quintessential example of a binomial random variable would be tossing a coin a certain number of times and counting the number of heads. If you know ahead of time how many times you're going to flip it, in this case, in this example 10, then n is 10. You know ahead of time there's going to be 10 trials. Every trial is either heads or tails, so there's only two outcomes on each trial, and so on. Probability of success is the same on every flip of the coin, and the coin flips are independent of one another. But you could also have a lab that's processing 100 pregnancy tests, and each pregnancy test is either positive or negative. So there's a lot of different situations that fit into this binomial setting. So here's an example. Suppose we flip a coin 3 times and observe the number of heads in those 3 flips. But suppose this coin is unfair, so that the probability of heads on each flip is 0.6. So, checking the bullet points from up here, we have 3 independent trials. Independent because one flip of the coin does not affect the outcome of the other flips of the coin. There's 2 outcomes on each trial or each flip, heads or tails. And the probability of success, which in this case is the probability of heads, is 0.6, and it's going to be 0.6 for each of the 3 flips or each of the 3 trials. And we're counting how many heads we get within the 3 flips. So let's find the probability that the number of successes or heads is 0. So plugging that into this formula up here, we have something that looks like this. The probability that the number of successes is 0 is 3 choose 0, and 0.6 to the 0, and 1 minus 0.6 to the 3 minus 0, which is 0.064. Now, there's a number of ways that you can calculate that probability. First of all, we've seen combinations on an earlier quiz, so you should all have a scientific calculator that will allow you to do the combinations piece of this. So if I use my calculator as a scientific calculator, I'm going to do 3 choose 0. And then I'm going to multiply that by the probability of success, which is 0.6, to the 0 power, using parentheses there to indicate multiplication, and then 1 minus the probability of success, which we also call the probability of failure, that to the third power, 0.064. So that third power that you see there is the 3 minus 0 power that you see there. There's a couple other ways of getting that 0.064 answer. If you have not just a scientific calculator, but if you have one of the TI-84 calculators, the binomial formula is built in. If you press second vars and scroll down a ways, you will eventually find something that says binom PDF, probability density function, probability distribution function. Tell it that we have 3 trials. Tell it that the probability of success on each trial is 0.6, and tell it that we want to know the probability of 0 successes. Now, not some of the older calculators don't bring up that menu I was just on, and they just display this on the screen, and you're expected to know that the format is the number of trials n, and then the probability of success p, and then the value of x that you want to find the probability of. But anyways, that should give me the exact same 0.064 number. Also, another way of getting this without using a calculator at all is on our class webpage, there's a link to tables for our textbook. And if you click on that, it brings up these tables. And the very first part of this table is binomial probabilities. So in our particular problem, we have 3 trials. So we want to be on this part of the table right here for n equals 3. So this is the only part of the table we want to look at. And even to narrow that down a little bit further, we have on our problem a probability of success of 0.6. So we actually want to be looking right in here, and there's the 0.064 already calculated for us on the table. Now we can continue this train of thought and then figure out the probability of having 1 success. So that's going to be 3 choose 1, and then the probability of success to the 1, and then the probability of failure to the 3 minus 1. So if we've had 1 success, that automatically means we've had 2 failures. This should come out to be 0.288. Let's do that in 3 ways. So we can do our earlier calculation like this. So now we have 1 success. We're going to do 3 choose 1, and then the probability of success to the 1, and then the probability of failure to the 2. And this exponent and this exponent should always add up to the number of trials, which is 3. So this gives us this 288 number on this document. And or I could use in the built-in function binomial PDF, tell it the number of trials, the probability of success, and tell it that we want to know the probability of 1 success. And this will give us the 288 number also. Or if we want to use the table, the 288 is already on the table right here. Again, we're in the section for n equals 3 since we have 3 trials. We're in the column for the probability of success 0.6, and we're finding the probability of 1 success, which is that 0.288. And to break down this expression a little bit, 3 choose 1 because there's 3 trials and we're choosing one of them to be a success. And then since we've had 1 success, we have the probability of success to the first power. And since we've had 1 success, we've had 2 failures, 3 minus 1, so we have the probability of failure to the second power. So in a similar way, we can figure out the probability of 2 successes, either by calculator. So now it would be 3 choose 2. So 3 choose 2, and the probability of success to the 2, and the probability of failure to the 1, which is also 3 minus 2. So that gives us 432, or we can do the built-in function if we have this calculator, binom PDF, and get that same answer, or we can go to the table, and that 432 is already calculated for us right there on the table. And then just to round this out, find the probability of 3 successes. So on the table, the probability of 3 successes is this 0.216 number. So you see I have that there. Or by calculator, probability of 3 successes would be 3 choose 3. 3 choose 3. And then the probability of success to the 3rd power. And then the probability of failure to the 0 power. Because if you've had 3 successes, then you've had 0 failures. So that's the same 216 number, or using the built-in function on this calculator, put a 3 there. We want to find the probability of 3 successes, 216. So probability of 3 successes is 216. And if we take these probabilities we just figured out, the probability of 0 successes is 0.064, and so on, and put them in a table, we get a table that looks something like this. These are the number of heads I could observe. I could observe 0 heads, 1 head, 2 heads, or 3 heads. And this is the probability of each of those values of x occurring. And just like in our other examples, all of these probabilities should add up to 1. And if I wanted to be a little bit lazy, I could have used that to my advantage and save a little bit of work. Once I had these first 3 probabilities figured out, I could have just added them up and subtracted from 1, and that would tell me what the last probability had to be without doing any calculations. But of course, all of these numbers here are right next to each other on the table right in here. So the advantage of the table is that the probabilities have already been calculated for you. The disadvantage of the table is that if our probability of success was not such a nice number, like if it was 0.64 or 0.65 or 0.66, we would not be able to use the table. The probability of success has to be kind of a nice-ish number like 0.6 or 0.7. The other thing is this table, we'll see in another example, if we scroll down this table, it only goes up to an n of 20. So if the particular binomial problem had an n greater than 20, you would be kind of out of luck with the table. But luckily, all of the homework problems have a value of n and a value of p that will allow us to use this table if you would like to use the table. Sometimes, since these probabilities here have to add up to 1, it's not uncommon for a quiz problem or such to give us this table with one of the probabilities missing. But that's no big deal because we can easily figure out the missing probability because we know that all the probabilities have to add up to 1. Okay, here's another example with a little bit bigger value of n. Suppose we have a random sample of 18 computer science students, 18 AP computer science students, and each student has a 0.75 probability of passing the AP exam. And since they were selected at random, we assume that the results are independent of one another. What is the probability that 15 of them pass the exam? Well, let's do this by the table first. We have 18 trials because there's 18 kids taking the exam, and the probability of success, the probability of passing the exam, is 0.75. So if we go over and find the right part of the table, gotta scroll down a little bit to find where n is 18 on this table. So here's the section for n equals 18, and the probability of success is 0.75, and the problem said, what's the probability of 15 successes? it's already been calculated for us right there, 0.170. Okay, and if we want to use the calculator to verify that, then we can do this calculation. On any scientific calculator, we can do this calculation. So the number of trials is 18. We are choosing 15 of them to be successes. We have the probability of success, which now is 0.75 to the 15th power, which means we have the probability of failure, which is 1 minus 0.75, and that's going to be to the third power. So there's 18 trials. If we've had 15 successes, then that means we've had 3 failures, and hopefully we see that this turns out to be the same 0.170 answer. Or we could use, if we have the TI-84, we can use the built-in formula for binomial and tell it that we have 18 trials, tell it that the probability of success on each trial is 0.75, and that we want to know the probability of 15 successes, and that's the exact same number. So somehow, some way, either using a calculator or using the table, we need to be able to figure out that that 0.170 probability. So the next question says, what is the probability that more than 15 of them pass the exam? So if more than 15 of them pass the exam, that either means we've had 16 successes or 17 successes or 18 successes. And on a problem like this, the table is almost easier because the probability of 16 successes, 17 successes, and 18 successes are right next to each other on the table. So we bring up this table. The probability of 16 successes is 0.96. The probability of 17 successes is 0.34. Probability of 18 successes is 0.06. So we add those probabilities together, and we get an answer of 0.136. Next part says, what's the probability that less than 10 of them pass the exam? So technically, if less than 10 of them pass the exam, I got to add up the probability of 0 successes, plus the probability of 1 success, plus the probability of 2 successes, 3 successes, etc., 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 all the way up to 9 successes. But luckily, most of those probabilities are 0. If we take a quick look at the table, so I'm adding up all the probabilities from 0 successes all the way up to 9 successes. So most of those probabilities are 0, 0, 0, 0, 0, until we get to the probability of 7 successes, that's 0, 0, 1, 8 successes, 0, 0, 4, and 9 successes, 0, 1, 4. And so I pop those numbers in here and add them up, and that probability is 0.019. Some of these other probabilities that say 0 plus, it says 0 plus because the probability isn't really 0, like this one here for the probability of 6 successes. If we go back to the calculator, for the probability of 6 successes, 18 trials, probability of success 0.75, and the probability of 6 successes. It's not 0, but it's a number small enough that it's written in scientific notation. So this is actually 0.00019, and because our table is giving us probabilities to only 3 decimal places, it appears on the table as though it is 0. Okay, the next question was, would it be unusual to observe less than 10 of the 18 students pass the exam? And we just figured out that that probability is 0.019, which is about 2%. So my answer would be, yes, this is unusual because the probability of this happening is only about 2%. We'll get into, in a later chapter, we'll get into the exact percent that statisticians refer to as quote-unquote unusual, but usually that cutoff is at around 5%. So let's see how all that plays out on one of the homework problems. So, because you guys have not yet finished Chapter 5 homework, I've given you guys until Thursday evening to do the Chapter 5 homework. I'm going to bring up the Chapter 5 homework. Public Health Organization reports that 25% of baby boys in the United States weigh more than 20 pounds. A sample of 14 babies is studied. So our probability of success, quote unquote, is 0.25, and the number of trials is 14 because we have a sample of 14 babies. And what we're calling success in this problem is a 6 to 8 month old weighing more than 20 pounds. So our N is 14 and our probability of success is 0.25. What's the probability that 5 of them weigh more than 20 pounds? So we go to our table. Now there's a little link right here in the problem that'll bring up the table. So we need the part of the table for N equals 14. See if I can zoom a little bit when we get there. We need the part of the table for N equals 14. Okay, and then we need the column of the table for a probability of success of 0.25, which looks like it's the fourth column. So let me scroll down here a little bit and zoom a little bit. So the fourth column over is for 0.25. So we want to be living right in here. In particular, this column right here. So it said, what is the probability that exactly 5 of them are successes? So here's 5, N is 14, 5 successes, probability is 0.147. The next part of this, what's the probability that more than 2 of them weigh more than 20 pounds? So more than 2 of them means we have either 3 successes, 4 successes, 5 successes, all the way up to potentially 14 successes. So it says more than 2 of them, which means I'm going to start off with 3. Let me bring up my other calculator here. So we got this probability 240, and then add 220, add 147, add 073, add 028, add 008, and add 002. And that looks like the end of the road. And that is 718. So let's go back to our problem here. It looks like that's going to be 718. And there's actually, it's a little bit tricky sometimes to think about, but there's actually another way I could do this. Instead of figuring out the probability of more than 2, let's add up all the probability up to 2 and then subtract from 1. So I could have done this. I could have said the 0.018, which is right here, plus the 0.083 plus the 0.180, I could have got that answer and then subtracted that from 1. 1 minus 281, and that's the same 719 answer. Okay, next part of this question says, what's the probability that fewer than 2 weigh more than 20 pounds? Fewer than 2 means either 0 of them or 1 of them, which is only this probability here and this probability there. Fewer than 2 means we've had 0 successes or we've had 1 success. So now I just want to add together the 0.018 and the 0.083. So that's going to be 0.101. And then the last question, would it be unusual if more than 6 of them weighed 20 pounds? So let's go back to the table and see what's the probability of more than 6 of them weighing more than 20 pounds. So more than 6 of them. So that would be starting at 7. More than 6 of them means we start at 7. So that's 028 and 008 and 002. So the probability of that happening is 038, which is kind of small. So I'm going to say that this would be unusual for more than 6 of them to weigh more than 20 pounds, since the probability of that happening is 0.038. So that's kind of how the homework problems are going to go on binomial. So hopefully that's enough input for you to be able to get the last part of that homework done. Again, homework 5 is due this Thursday at midnight. So get working on that, and we'll be talking to you soon.